last test. I still don't know who designed that idea. Anyway, so I guess to introduce it or something, no clue. So we're doing that. I'm getting burnt out. I don't know about you guys. People ask me some days, do you love chemistry? Well, yes, some days. Today's not one of those days. Today's like, does chemistry have to exist today? And I'm tired and I'm stressed. It's the end of the semester and I get nervous about things, which is crazy. You wouldn't think I would because I don't have to take them, but I still do. Memorizing, yeah. It's not, but I'm going to put it on D12 for you guys. So that might be kind of nice for you guys. This is a little bit more information than the textbook, but the textbook has a little bit more information than the slides, so I guess we'll put them together and it should be all right. That's true, Amelia. Physics lab was kind of fun. Physics itself. Some of the questions are rather hard. I think I had one on a test, and it was a bullet on Gettysburg Field is flying at this angle and this speed, and this other bullet is flying at this angle and this speed, and they come together and they hit each other mid-air and fuse together. What direction and how fast will they be going now? And I remember looking at the test thinking, are you kidding me? First of all, who cares? You know, that was my least favorite question ever. Then when I figured out how you do it, which I can't even remember how to do it now, but at the time when I realized it was like, oh, it's just triangles. But during the test, which was when I needed to know it, I couldn't figure it out to save my life. Oh, that's funny, exactly. All right, so let's get started with the dissolution of ionic compounds. So, what happens when you have ionic compounds, like sodium chloride, which is like table salt, and you put it in water, it will dissolve. And with some other solid substances like sugar, when you put it in water, it will dissolve. But they don't do exactly the same thing in the way they dissolve. Because with sugar, all the elements are covalently bonded. In other words, they're pretty stuck. With ionic compounds, they're not sharing any electrons. One has stolen the electron from the other one. And so when they get into water and water surrounds them, the water captures each ion individually. So the ions will break up. And so you'll have like a sodium over here, a chlorine over here. And then the water will orient. So the hydrogen will orient toward the negative piece and the oxygen orients toward the positive piece. And there's just kind of a picture of what that looks like there. At least on the molecular level, because, you know, it looks nothing like that when you put it in glass. If it did, I don't think anybody would be too interested in salt water. It'd be like, ugh, I don't want to drink anything green. It happens with ionic compounds and acids. And that's why they put them together. It's because, and electrolytes. So ionic compounds, electrolytes, and acids. And I'll tell you what electrolytes are in just a second. So ionic compounds really make electrolytes. So here we have information about electrolytes and non-electrolytes. A big thing about electrolytes is that they're ionic compounds dissolved in something, usually dissolved in water. And so if you put a battery and a light bulb and all that, you set it all up like that. If you take the probes out of the water, there's no connection between the two probes. And for electricity work, think about it like if I have a remote control car that runs on a battery and I take out the battery, it won't run. But what if instead I left the battery in and cut the wires? It still wouldn't run. And the reason is because the electricity will only flow and then stop. So it's got to flow all the way around the whole circuit constantly in order to keep whatever it is charged. Not charged, but working. So if you look on the left, the light bulb on the left has table salt, sodium chloride in it, and it's forming an electrolytic solution or an electrolyte. And the electrolyte keeps the current going. So you see how the light bulb has a wire that goes to the battery, from the battery to one probe, which would be that long black stick there, and then water, and then the black stick, and then a wire back to the light bulb, and the light bulb is lit. It's working. And it's bright. The reason it can do that is because it's transferring charge in the ionic solution. So moving charge is what current is. It's moving charges. And so they can move through the solution because there are charges in the solution, keeping the electrons flowing. On the right-hand side, there's sugar in the solution, but there are no ions at all. This is a theoretical situation, so in reality, if you use like water from your tap, there's all kinds of ions in there because they put lots of stuff in there. They put fluoride in there for your teeth, and they put chlorine in there so you don't die of whatever's in the water that they purified from the sewage and whatever. So there's a lot of chloride. There's a lot of ions in tap water. So if you put a light bulb like that in regular tap water, it might still light. But if you put it in theoretically pure water, which you probably won't come in contact with, the light bulb shouldn't light at all. DI water, kind of like DI water. It depends on how good your filters are with DI water. For example, I used to work in one lab, and they had a lot of money. So their DI filters were changed a lot. So it got a lot of the ions out. Not every single one, but most of them. Then I worked in this other lab, and they wanted me to test the conductivity of the solution after running it off of some electrical plates or something, some circuits, to see if there was something wrong with the circuitry. Was it holding the charge it wasn't supposed to, or something like that? So I was testing that solution, and the conductivity was high. And then I checked the water by itself, and the conductivity in the water was high because their filters were like 4 or 5 months old, and they said they couldn't afford new ones. And I'm like, well, how am I supposed to do this experiment? That's crazy. Yeah, pure water should not conduct electricity. But just a warning, you're not going to run into pure water outside a lab where it's producing it. Even if you're working with DI water, it won't be completely pure. How does salt conduct electricity? So how it does that, let me go back a slide or two, and I will show you how that works. All right, so looking at this, you see how it's got the plus? That will be the sodium. The purple ones are the sodium. And the minus ones are the chlorine. So when electricity is flowing, electrons are flowing. So they have to be able to kind of move through the solution. So they can kind of come through the solution and get onto the chlorine, and then the water can move them, and then they can move to another chlorine, and then they can move to another chlorine, and they can move to another chlorine, until finally they get to the other probe, and then they can move through the wire. Now, there are probably lots of electrons moving around in solution. It's not like one perfect stream of electrons moving through solution. It's just some of the electrons are going to move out of one probe, and the other probe is just going to be picking up the excess of the electrons that are moving around. And so then the current will continue on from there. So the current is moving all through the water, and then the other probe will pick it up from the water and move it on toward the light bulb, if that makes any sense. And so an electrolyte is something that will light the light bulb. And non-electrolytes will not light the light bulb because if they're in pure water should not conduct electricity because there are no ions in it. And if you put if you put sugar in it, sugar's not ionic, so you still haven't added any ions. So the electricity won't flow and the light bulb won't light. So to have an electrolyte solution, you have to have ions dissolved in the solution. So it's more or less a salt solution. When I say salt, salt doesn't mean, sorry, I wish this would go away. There's Teams just keeps popping up, sending me messages, and I'm like, stop. Yeah, a salt is any ionic compound, right? So when I say salt, I don't just mean table salt. Calcium fluoride is a salt. Sodium bromide is a salt. So anything that's ionic is a salt. No, it can be any ionic compound. You can even have ammonium chloride, and that's considered a salt. Correct. Sugar is covalent, and it's not ionic, so it won't help electricity flow at all. So things that won't help electricity flow that don't have ions in them are considered non-electrolytes. And then they go a little bit further with the electrolytes, and they classify them as either strong electrolytes or weak electrolytes. And then we have strong acids and weak acids. In a strong electrolyte, all of the ions in the substance break apart. In a weak electrolyte, only some of them will break apart. Yes, I will. Yep. So strong electrolytes, all the ions will break apart. Weak electrolytes, some will break apart. So if you were to look at a light bulb being lit that was running current through a strong electrolyte, you'd get a bright light because the current is flowing easily. If you have a weak electrolyte, current still flows, but not as well. So you'll get a lit bulb, but it won't be as bright. And then acids and bases do the same thing, except they're not salts. They're acids, but they do the same thing. Here they're showing at the top is sodium chloride, strong electrolyte. And then at the bottom, they're showing a weak acid, which is acetic acid. And so go back to the sugar just so you can kind of see what's happening with the sugar. So the sugar as a giant molecule sticks together, and it has partially positive and partially negative parts, just like the water does. So the water will orient in certain directions and pull one molecule from another molecule, but it's not like going to pull the oxygen off. It's just going to pull one molecule away from the other ones. The water will surround it and orient so that the hydrogens are going to get the oxygen and the oxygens are going to get the hydrogen of the water. But the sugar molecules don't break in half or anything like that. I need to just Stop Teams. Okay. The dean is having a meeting with lecturers this morning, and it's nerve-wracking. They keep sending me messages. Yeah, I just shut it off. It's like, no more. Because he has multiple times to meet with lecturers, and today's not a day I can do it, so I have to do it later. But I don't want to just keep seeing his name popping up in the corner. It's making me nervous. Yeah, absolutely. I'll go up a slide. So the sugar one, I'm assuming you mean this one. Okay. Do you have a question about this one? Oh, you're good? All right. All right, so we went over sugar dissolving. Let's see. The last sentence. Okay. All right. And in acids, acids dissolve in water also, because acids have a positive hydrogen or multiple positive hydrogens and a negative piece. It can either be a negative polyatomic ion or a negative ion. And it depends on what type of acid you're looking at. Lewis acids and Lewis bases are different. You can have metals instead of hydrogens, and Lewis acids are a little bit weird. But we're not going to talk about them today. I think they're more of a 12-12 concept. But anyway, so with an acid, I guess technically they're molecules, but they're held together by an ionic bond between the hydrogen and whatever else. So the hydrogen gets positively charged, and whatever negative thing there is, like in this case, chlorine is negatively charged. When you put it in water, one of two things will happen. Either all of the ions will break apart, or only some of them will break apart. If you have all the ions break apart, they call that strong acid. If you have some of the acid break apart, that's a weak acid. Let's see. Correct. Strong acids should have the arrow pointing to the right because they just go in one direction and they fall apart. Weak acids, on the other hand, you can see they have two half arrows, one kind of to the right and one to the left. The reason is because constantly with weak acids, what happens is a molecule will fall apart into H plus and F minus. Then H plus and F minus will join together again and become HF. And then it will fall apart, and then it will join together. It will fall apart, then it will join together. So it's going in both directions at the same time. But the whole time there will be some of it in solution that at any one given point is dissolved. It just won't be the entire molecule dissolved all the time. I mean, the entire molecule will dissolve, but I mean, not 100% of the molecules will be dissolved when you measure it every single time. With a strong acid, 100% will be broken apart. They can both be poisonous, actually. In this case, I would be more afraid of hydrofluoric acid, which is considered the weak acid. I think hydrofluoric acid can dissolve bone, in addition to things like metals and stuff like that. Hydrochloric acid can dissolve some metals. It depends on whether or not it's going to react with the metal. But just because they use the word strong doesn't mean it's more harmful than the weak acid. The weak acid actually can be as harmful or more harmful than a strong acid. It just depends on what they are. If you want an acid to stop dissolving something, you would do one of two things. Either one, you would put lots and lots and lots of water in solution. or you would add a base. A base, like baking soda, would slow it down probably quicker than adding lots of water. Well, hydrofluoric acid is not stronger. It can be more damaging. It just depends on what it is you're combining it with. Because fluorine is so electronegative, it just becomes so nasty because it will react so quickly. So it will react with all kinds of things. HCl is quite nasty in and of itself. But just because it's weak, that's only referring to how much it ionizes, not how much it will harm you. And then we talk about strong and weak electrolytes. Boy, there's something weird with these slides, isn't it? It's like you don't get the first sentence. I wonder if you just download them, that might look normal. Let me check. Hang on one second. Most likely, you will. I'm trying to look and see if there's a list of them in your book. Normally, they have a list of strong and weak acids. Okay, yeah. All right, so if you go to the textbook, table 8.2 has some strong acids. There should be a list of weak acids there somewhere. Yeah, table 8.3 is some weak acids. So you should be familiar with those two tables. Because you might get a question and it might give a list of different acids and say, which of the following is a strong acid, or which of the following is a weak acid? So that kind of thing. Let's see, lower pH. So higher pH, lower pH. It really depends on how much H plus is dissolved in solution. So let's say I have 1 drop of hydrochloric acid in solution and I have a cup of hydrofluoric acid dissolved in solution. The pH of the hydrofluoric acid would be lower than the pH or the acid solution than the HCl. Now, if you took concentrations of both of them, and the concentrations were identical, the pH should be lower in the HCl. When the pH is low, that means it's more acidic. So as you get closer and closer to 7, that's neutral. Yes, actually, that is why it's weak. The attraction between the molecules is higher. Yeah, higher than 7 is basic. That's correct. The strong bases are a lot easier to recognize because the strong bases, it's pretty much anything with OH minus is a strong base. So like sodium hydroxide, calcium hydroxide, stuff like that. And normally the only weak base they make you memorize is ammonia. So it's a lot easier to remember those. Water is pH. Not sure what you mean by LVL. Oh, did you really? Cool. That's nice. Sodium hydroxide is kind of cool. When you mix it up from the pellets, it'll cause it to get warmer. Level. Okay. All right. LVL is level. All right. Got it. Thanks. All right. Strong acids will also conduct electricity, just so you know. Weak acids will conduct electricity, just like weak. Oh, that's okay. Just like weak electrolytes. All right. So then they have 2 different words for the same thing, and I don't know why they bother. Just give it 1 word and let it go. But no, they have to do it differently because they're scientists. So dissociation and ionization. When you have an anion and a cation and they separate from each other, they call that dissociation. So ionic compounds dissociate. When you have an acid, it will ionize. But it's the same action. Different word. Just like molecule versus formula unit. Molecules for covalently bonded things and formula units for ionic bonded things. So dissociation refers to ionic things falling apart, and ionization refers to acids falling apart. All right. So here's just a picture of, kind of how you can see what these different things look like. So if you have a non-electrolyte, you can see the light bulb is not lit. If you have a weak electrolyte, it's lit, but not very bright. Actually, what they have there is weak acid, which does form a weak electrolyte. And then they have sodium chloride, which is a strong electrolyte, and that lights up quite brightly. Most of the time when they have a weak acid, like the acetic acid that they have there in the center, they don't call it a weak electrolyte so much as they call it a weak acid, but it will form a solution that will conduct electricity. So technically, I guess you could consider that a weak electrolyte. All right, so that's that part. We're not going to get into solubility today. Solubility is my least favorite topic. It's because there's so many rules, and I hate memorizing stuff. And you have to memorize the rules, and there's not a big pattern to them, which bugs me. I like things with patterns because they make sense to me. No pattern, just was like, why even learn it? Which is stupid because there are lots of reasons to learn it, but that's exactly where my mind goes. It's like, why bother? So, all right, let's see. Where were the notes it's going to go through? Okay. Let's see here. All right, let's find out where. I'm trying to find out what I'm sharing. Oh, nothing at the moment. Okay. I wonder if I closed that slide. Hopefully not. Okay, try that again. Okay. It's telling me my connection's not good enough to share anything right now. I'm like, you've got to be kidding me. I'm going to reload the session, so give me just a second. I may disappear, but I'll be right back. All right, I'm back. Let's try this again. There we go. All right. Yeah, what's it? I didn't have to close out of it. I just had to click reload. For some reason, reloading is quick. I don't know why. If I tried to reload it normally, it would be super slow. All right. So this set of notes goes over the sections that I just showed you, but it may have a little bit more information, so I'm going to just kind of go through it. If you look at the top, you'll see sodium chloride is falling apart into sodium plus and Cl minus ions. A lot of times what you'll see is instead of sodium chloride and then the little aqueous symbol means it's dissolved in water, or it's in water. A lot of times you'll see NaCl, and that'll be solid, and above the arrow will be written H2O. And what that's indicating is that solid sodium chloride mixed with water and formed Na plus aqueous and Cl minus aqueous. And then I've just got a little arrows showing you what's attracted to what. So the chlorine will be attracted to the hydrogen because it's negative and partial positive, and the sodium is positive and the oxygen is partially negative. And solutions that come from dissolved ionic compounds are called electrolytes, and electricity passes through. So that's just kind of a review thing there. Okay. See if there's anything here that I want to go over. These are solubility rules, but we're not going over those today. Precipitation reactions, also hate those. I mean, they're exciting. They're wonderful. You should really look forward to next week when you get to learn those. I should be a little more positive today. So grouchy today. I'm positive I don't like those types of solutions. It's like, that's not helping anyone. Okay. So if you look here, it's just showing you that we've got acids, strong acids and strong bases and kind of what they look like. It's really not that hard, Chad. I'm making it sound like it's hard, super hard and miserable. It's not. It's a short list of rules that you just have to memorize. I just don't like to memorize things, which is the reason I don't like biology, because I don't want to memorize anything. I like the idea of studying living things, but I just don't like to memorize anything. I guess it's a little bit of laziness in there, and partly because when I memorize stuff, I don't ever remember it. It's there for till the test and gone. Sometimes I don't even make it to the test. So usually it makes it to the test, and as soon as I walk out the door, information gone. So I feel like for me, considering that's the way I do when I memorize things, I wonder what did I bother with that for. So, all right. So the main thing, when you get to the solubility rules, if you look down, you see the first sentence there is acids are molecular compounds which do ionize. In other words, they fall apart. Strong acids dissociate. Look at how I've got the two words. I'm using them wrong here, because if acids ionize, down here I should have strong acids ionize completely and weak acids ionize partially. But anyway, so then weak acids are weak electrolytes, and then it says not all ionic compounds dissolve in water. Some of them don't. So if they're soluble, they dissolve in water. If they're not going to dissolve in water, they're called insoluble. In is a prefix that means not. So it's just basically saying soluble and not soluble. And then when it comes to the solubility rules, these are the solubility rules. So you have to remember this information. But there are some patterns in this that it's not so bad. And I'll go through that next week. It's like certain columns of the periodic table, that stuff's soluble. Certain ions are not soluble unless you mix it with something that's always soluble, and that kind of thing. But we'll go over that next week. Let's see what else. See if I've missed anything I wanted to share. So I'm going to switch over to the textbook now. All right. Let's see here. Are we done? Almost. We're almost done reading. Look, are we done yet? Please tell me we're finished. If I get done early, though, I'll let you guys go early. Okay, so let's take a look at section 8.3 to make sure I didn't miss anything. All right, in your textbook, this is what you'll find in section 8.3. Let's see. All right, so it's showing how pure water doesn't light anything up. So they have all this stuff. They have, the first one, it's just water. No ions, just water. And the light bulb doesn't light. The next one has a lot of, what the heck does it have in the second one? Okay, the second one has sodium chloride in it, but it's solid sodium chloride, which you can't really see in the picture. So what they're saying is if you took these probes and you put them into a salt shaker without adding water, nothing's going to happen. there has to be some charge separation in order for current to flow. By charge separation, I mean the positive and negative cannot be right on top of each other. They have to be slightly separated in order for the current to flow there. Oh yeah, you could use another liquid other than water. Generally, they talk about water the most. Water is considered the universal solvent. It doesn't really universally dissolve everything, but it dissolves a lot more things than you would expect. It's actually one of the best solvents. And they do a lot of experiments in the lab that'll show you that you'll use this chemical solvent and this chemical solvent, and you'll test it with all this stuff, and then you'll test water with all this stuff, and you'll go, oh wow, water dissolves all kinds of stuff. So they call that the universal solvent. And then, let's see, in box C, they're showing dissolved sodium chloride. In box D, they're showing ethanol. Ethanol is just a hydrocarbon that's an alcohol. Since it's molecular, no light there. And then in the very last one is acetic acid. And so you have acetate, CH3COO minus, and hydronium, which is H plus. They don't really explain that very well there. We'll get into the hydronium later, though. Yeah, and so the weak acid doesn't light the light bulb quite as well. It talks about the direction of current flow. The sodium ions are attracted to and move toward the graphite rod or electrode connected to the battery's negative terminal. So they're just talking about the direction that it flows. So it's good to read through this. It's got a little bit of good information here. We talked about strong and weak electrolytes and non-electrolytes. Hydronium, they kind of explain a little bit. So you have water, which is H2O, and you have an acid, which is HCl. When the acid falls apart, you get H plus and Cl minus. Then the H plus will attach to an H2O and become H3O plus. So H3O plus is identical to H plus. Sometimes they'll say measure the H plus in water, or not in water, in this acid. And other times the same question will be read, measure the H3O plus. So they're used interchangeably a lot of times. Heavy water is made with deuterium instead. Well, it is deuterium. It's made with heavy hydrogen. It's hydrogen with, I believe, an extra neutron. So you can have tritium, which I think has 3, and then deuterium has 2. Look that up real quick. Make sure I'm giving you the right definition. Yeah, that's right. So you add more neutrons so that it weighs more. Obviously, you don't add more protons, because if you did, it wouldn't be hydrogen anymore in the water. But the hydrogen, when it has more neutrons, is heavier. So when they have hydrogen ions, not ions, isotopes, hydrogen isotopes mixed with oxygen, then it'll form heavy water. It's just made with isotopes of hydrogen instead of regular hydrogen. It's a good question, though. All right, let's see. And we worked with strong and weak electrolytes, hydronium. All right, did all that stuff. Absolutely, yeah, no problem. I will try to do that today, this afternoon. I've got a meeting that I'm not looking forward to this afternoon. But after the meeting, I should be able to spend a little time adding some tutorials, either this afternoon or this evening. But yeah, I'll put some on there. All right, we got acid-base reactions, which is proton transfer. The first thing, it's not due until like next week. So if there's a due date showing this Sunday, ignore it. Nothing is due Sunday. So, I mean, some of your bonus work, I think, is due Sunday. If you look in the announcements on D2L and scroll through the announcements, you'll see the bonus work for the exams. So kind of look through that. I think one is due Saturday, one is due Sunday, and then something like that. So, yeah, no adaptives are due Sunday. I'm changing the due dates because we've only gone over 2 sections. So I'm going to wait until closer to the exam. I'll probably have all the homework due around exam time, actually. But I'll let you know more about homework. I've opened it up so you can take a look at it, and if you want to work on it, that's not a bad idea. But it's not due on Sunday, so I don't want you to think that you have to do all that by Sunday. The other ones you missed. Actually, I haven't opened those, I don't think. Have I opened those for you guys? Cannot remember. No. Okay, well then, yeah. So they're not due on Sunday. I'll spend time this afternoon too. Either this afternoon or tomorrow morning. I will open up those adaptives. They will be half credit. They will be open by tomorrow at noon. When you do the adaptive, though, it's not going to show a late penalty. So even though it might show that you got 100 if you do it tomorrow, it won't stay 100. So I'm going to have to go through them once you do the adaptives, and everybody that did it after a certain date, that'll be considered half credit. So I didn't want you to like get excited about the grade and then disappointed about the grade. Just if you do it, you know, from now on, it would be half credit. It is better than 0 though. Yes, as long as it's not like, and I don't think you do this, Chris, but just, to give a blanket statement to the whole class, you can't just leave the adaptive on for an hour. You have to actively be working for an hour. So you have to, be going through some questions. So. All right, let's see. You're welcome. For the bonus, it says to work through the whole chapter. Does that mean that we do all the questions throughout rather than just, yes, that is true. So the only ones you have to turn in to me are the practice questions. But the reason I want you to do the whole chapter is because when you do the whole chapter, first, well, the chapters are pretty short. So it's not like a chapter in our textbook. It's just a few pages. But you read through that information, and then it will give you a few practice questions. You try those practice questions, and then it will give you the answer and an explanation for the answer. Now, when you do the practice questions at the end of the chapter, like the little practice test they have at the end of each chapter, those questions, it'll give you the answer, but no explanation. So if you do the practice ones inside the chapter, that gives you a better understanding and so a better ability to do the other questions. Yeah, there are a lot of them. Yeah, so just submit the practice questions. Yeah. If you're running short on time and you're able to do the practice questions on your own, do the practice questions and go back and do the chapter later and then redo the practice questions again. I would recommend doing this consistently until the final exam. Just keep working at it. I mean, don't like throw away all your other classes so you can study that. Not that anybody would, but that's not what I mean by that. I just mean like continue to spend a little time. Don't just go through like the first chapter and say, oh, good, I did it, I'm done. What I want you to do is go through it, then study chapter 2, then study chapter 3, or whatever chapters we went over. and then go back when you're done and start again. And especially spend time on the stuff that you found to be difficult. A lot of people find that to be the Vesper structures, valence bond theory, stoichiometry for sure, solubility rules, but we haven't learned those yet. They don't find the solubility rules to be hard, it's just you gotta memorize them, so that takes a little bit of time. Sometimes naming stuff, but not usually too much on naming stuff. Those chapters are from the ACS book, that is correct. If you don't have an ACS book, you can get together with the other people in class. I am perfectly fine if you guys get together to work on the ACS practice questions together. Just don't turn me in one set of questions with 6 people's names. So everybody's got to turn in the questions and turn in their work. But if you want to get together with, like, heck, if the entire class got together, I don't care. But I do want you, I don't mean I don't care, that's a bad phrase. I am fine if you guys want to work together on it. It's actually good to be able to work together on it. But if you don't have one, then you can, I guess, talk to a REAP. You got one for free. But you can also talk to other people in class, and they can share. I would think. I don't think they mind. Oh, there's a PDF. Okay. All right, and that's all I've got for you guys today. If we missed anything in section 8.4, we'll go over it again on, not the whole section, but we'll go over anything we missed on Monday. And next week, thank goodness, we're only going over one section a day. It's going to slow down just a little bit.